In this video, we're going to be looking at infinite geometric series. So the first question we have is find the sum of 1 plus 1 over 5 plus 1 over 25 plus 1 on 125 plus so on. So the first thing we need to recognize is this is really just the series for a geometric sequence. And what I mean by that is if I list out all the terms are 1, then 1/5, then 1 on 25, then 1 on 125. And what you notice is between each term, the common ratio is simply 1/5. So to go to the next term, you have to simply times by a fifth. And if you have a geometric series, where your value for r, or the common ratio, is in between -1 and 1, that means this series is convergent. Okay, that means it will converge to a single value. So we need to work out what does this summation actually sum up to. And one way we can do that is we can use the series formula for a geometric sequence. And the formula that I have gone through is a times 1 minus r to the power of n all over 1 minus r. And in this case, we have to state that r is in between -1 and 1. Okay, so it has to be a decay growth. So now that we have this formula here, let us identify what happens if we take the sum of all the terms, all the way to infinity. So that would simply equal to a times 1 minus r to the power of n all over 1 minus r. And again, r must be in between -1 and 1. So now that we have this formula here, okay, we can say that n is simply 1,000. So we can replace the n with 1,000 there, or sorry, n is infinity, so we can replace the n with infinity here. And r to the power of infinity, because we have a decimal to the power of infinity, so let's say 0.5 to the power of infinity, okay? If we take the limit of this, if we take the limit as n approaches infinity for x to the power of n, okay, where x is in between, or in this case we'll say r, where r is in between -1 and 1, we can say the limit will simply equal to 0. Okay, the limit will simply approach 0. So what we can say is the term r to the power of infinity is really just the same as 0. So r to the power of infinity is 0. So we get that the infinite series is a times 1 minus 0 divided by 1 minus r. So that means the sum of infinite terms in this sequence is the same thing as a on 1 minus r. And this is your formula for an infinite geometric series. Okay, so it's a over 1 minus r. You can work out the sum of infinite terms in that sequence by simply using this formula here, given that r is between -1 and 1. So let's go back to this question here. Okay, so now that we know that the series formula for infinite terms is a on 1 minus r, okay, what we can do is we can simply employ this formula. So we can say that the sum of all infinite terms in this sequence here is simply the first term in the sequence, so a, which is 1, divided by 1 minus the common ratio. And the common ratio here is simply 1/5. So if we work this out by hand, you can say this is the same as 1 over 4/5, which is also the same as 5 over 4. So the sum of infinite terms in this sequence, it will converge to 5 on 4. It won't exactly equal to 5 on 4 because you're adding infinite number of terms, but it will converge to this value here. So that's how you work out the sum of infinite terms or an infinite geometric series. Okay, this is our next question. So we're required to find the sum of infinite terms of this sequence until infinity. So we know that the summation series for infinite geometric series is just a over 1 take r. So first, let's actually verify this is a geometric series. So what we would need to identify is what is the common ratio? Is there a common ratio between each term from the previous? Well, if I take -2 on 3 and I divide it by 1, that's the same as timesing by -2 on 3. And the same thing here. To go from -2 on 3 to 4 on 9, I have to times by -2 on 3. So that means our common ratio is -2 on 3. So now we can work out the summation series. The summation is simply 1 over 1 minus the common ratio, which is minus 2 on 3. That would equal to 1 over 1 plus 2 over 3, which is really just the same thing as 5 on 3. So if I do 1 over this, that's the same as 3 over 5. So the series is convergent at the point 3 on 5. The sum of infinite terms in this sequence will equal to 3 on 5 because r is in between -1 and 1. And that's how you do this question here. Okay, this is our next question here. A rocket is launched in the air so that it reaches a height of 200 meters in the first second. Each second after the first second, it will gain a height 6% less than the previous height. So our question here is, what is the total height that the rocket reaches? So this looks like a complicated question, but what we can recognize is we are given an initial condition, an initial height in the first second, and then we are told each second it loses 6%. We are told that it loses by a ratio of 6%. So we can really times by 0.94 for each rocket height. And that'll give us the next second's height of the rocket and the next second's height of the rocket. So in other words, we can say we have a geometric sequence, okay, where we have the value of A is just 200. So in the first second, it's 200 meters. And then it gains 6% less height. So 0.94 times the 200 of the initial, and then we can do that to the power of n take 1. That's how you can work out the height at any given second. But because we know that we want to work out the total height, we actually want to work out the series. Okay, and the total height, we can clearly say that it won't just continue going up and up and up forever and ever. Rockets don't do that. Rockets will go up, but then they'll tend to only gain a maximum height and then fall back down again. So they'll reach some sort of maximum height. So our goal is to work out what is this distance traveled from bottom to top. And we can use an infinite geometric series for this. Okay, so if we want the infinite geometric series, okay, because r is in between -1 and 1, okay, we can use the infinite geometric series, a on 1 take r. And what that will give us is the initial height reached is 200 meters divided by 1 minus 0.94. And if we work this number out, we get 3,333.33 meters tall. So this is the height of the rocket that it will reach. It won't continue going past it, but it will converge to this height here before eventually falling back down. Okay, so that's how you use an infinite geometric series in this question. A man walks 3 kilometers in the first hour of a journey, and each subsequent hour that he walks, he completes half the distance of the previous hour. So if he walks 3 kilometers in the first hour, the next kilometer, he will complete 1.5 kilometers. And our question is, can he complete 6 kilometers worth of total distance of walking? Well, the first thing we need to recognize is because our common ratio is a half, okay, because if we have a sequence, he walks 3 kilometers in the first hour, then half the distance in the next hour, then half the distance in the next hour, and so on and so on and so on. We can recognize that the common ratio is a half between each term. So that means if we were to take the summation of infinite terms in the sequence, it would be convergent at a single value. So we can work out the summation of infinite terms by doing a on 1 take r. So if we do this, we can say that the initial distance that he walks in the first hour is 3 kilometers. And we can divide that by 1 minus the common ratio. So how much does the distance decrease by each hour? It decreases by a half. So that would mean that 3 divided by 1 minus a half is the same as 3 divided by a half, which is simply 6 kilometers. So can he complete a 6 kilometer walk? Yes, he can, because the infinite geometric series says that he will actually approach 6 kilometers. Okay, this is our next question. So this question says that a frog stands 10 meters from the edge of a pond. Okay, so if we have a pond, just to visualize it, this is our pond, has some water in it. And there is a nice frog 10 meters away. So this is a frog. I don't know how to draw, but that's a frog. And it is standing at a distance 10 meters away from the pond. So its first jump towards the pond is 2 meters long. So it'll travel 2 meters towards the pond. Then it'll travel 1.5 meters. then 1.25 meters and so on, 1.125 meters and so on. So if it continues this pattern, we have to work out whether or not it will actually reach the edge, and we know the edge is 10 meters long. So the first thing we need to do is we need to create a sequence. Okay, so we know that it goes 2 meters in the first bounce, then 1.5 meters in the second jump, then 1.125 meters in the third jump, and then so on and so on. So if we work out what the common ratio is between each of these terms here, we can say that from the first term to the second term, you had to multiply by 3/4. And then to go from the second term to the third term, you simply do 1.125 divided by 1.5. Okay, and that is also the same as 3/4. So we've identified that the common ratio is 3:4, and the initial condition is 2. Because the value of r is in between -1 and 1, we can say that if we take the infinite series of this sequence, then it will actually converge to a value. So we can say that this sum to infinity is simply equal to 2 divided by 1 minus 3/4. And we can do this, again, because the value of r is in between -1 and 1. And if we work this out, that's the same as 2 divided by 1/4, which is the same as 8 meters. So even if this frog continues to bounce and jump closer towards the pond for an infinite number of jumps, it will only ever travel a total distance, or a maximum distance, I should say, of 8 meters. So that means because the length of the distance between the frog and the pond is 10 meters, it's actually unable, it will never reach the edge of the pond because it'll travel 8 meters even though the distance is 10. So that's how you do this question here. Okay, this is our next problem. So a stone is skipped in river, and each skip that it does, it travels 30% less distance than the previous skip. So how long should the distance of the first skip be on the river so that the total distance that the rock actually travels is 40 meters? So what we can identify here is the distance decreases by a same ratio each skip, so by 30%. So we can say the value of r is 0.7. And the reason we're saying it's 0.7 is because 30% less actually means 0.7 times. Okay, so 0.7 times is the same as 30% less. So that's why the ratio is 0.7. So how long should the first skip be? Well, we know because the value of r is in between -1 and 1, if we take this skip of the stone on the river an infinite number of times, it will converge to a point. So we can use our infinite summation. So the sum to infinity equals to a on 1 take r. Okay, and we know that the sum to infinity, okay, we know the total distance traveled after an infinite number of skips is going to converge to 40 meters. And we don't know what the initial distance is, the initial distance of the skip, so I'm going to leave this as a. But we know that 1 minus r is really the same as 1 minus 0.7. And the reason for that is the ratio was 0.7. So we can say on the bottom 1 minus 0.7 or just 0.3. So now to work out the distance traveled by the initial skip, the value of a, we can just times both sides by 0.3. So when we do that, we get 40 times 0.3, and that's the same as 12 meters. So this is the distance of the initial skip. This is how long this initial skip should be. Okay, this is our next question, and it's very similar to the one that I did in my geometric series video, so go have a watch of that before you watch this question here. A ball is dropped from a height of 15 meters, so that's dropped from a height of 15 meters, and it rebounds from the ground at a height of 10 meters. So in other words, it's dropped from this building and it bounces back up to a height of 10 meters. Each bounce, the height of the ball rises to a height of 2/3 the previous height. So as illustrated in my diagram, if you start at 15 meters, okay, the next bounce, the height it will reach after the first bounce will be 2/3. It will be 2/3 that of the original bounce. And then this pattern will continue. So 2/3 of 10 meters is 6.6 meters. And then 2/3 of this distance is going to continue. The pattern will continue forever. But as you can imagine, if you bounce a ball in real life, you won't just see the ball bounce forever and ever and ever and ever and ever and ever. What will actually happen is the ball will bounce. You can visibly see it bounces quite a bit after this, but then after a while, it'll just look like it's completely still. Okay, so what you can say is the distance of the ball has to converge to a value, not even because of any math related to this question, but just because of visual imagery that you've seen in real life. A ball will never bounce forever and ever. It'll always eventually stop and just remain flat. So now our question is, what is the total distance that the ball travels until it has reached rest again, until it's not moving? So let us now work this out. And the way I'm going to do this is going to be very unorthodox. I'm going to imagine that this is our starting point. Okay, imagine that this is our starting point. So we can consider both arches for 10 meters. So we can say the height that the ball reaches on T1, so the first bounce, is 10 meters. Then the second bounce is going to be 6.6 meters. Third bounce is going to be 2/3 of that, and so on and so on and so on. So if I have a sequence like this, okay, so 10 meters, 6.6, then 2/3 of 6.6, I can work out the sum of infinite number of bounces according to this pattern, because I know that the common ratio between each of these terms is simply 2:3. So what that means is because r is in between -1 and 1, so because r is in between -1 and 1, the summation of infinite terms here will converge to a single point. So what we're actually doing is we know that this height is 10 meters, and this height is also 10 meters. We know this height is 6.6 meters, and this height is also 6.6 meters. So what I'm going to first do is I'm simply just going to work out the sum of each of these bounces, so the down bounces each. And would you agree that those distances follow a geometric sequence? Well, yes, because the height of each of these red lines that I'm drawing is simply 2/3 of the previous one. So let us work that out. The sum to infinity, and I'll even write it in red. So we're trying to work out this distance, this distance, this distance, forever and ever and ever. So what we have is the sum to infinity is simply going to equal to the initial height, so 10 meters, divided by 1 minus the common ratio, which is 2/3, because each bounce is 2/3 the height of the previous one. So what we get is 10 divided by 1/3, which is simply just 30 meters. So this is the distance when the ball travels infinite number of bounces for these red lines here. It's 30 meters. But you would agree that a ball doesn't just bounce like this. It doesn't just go like this, then teleport here, then bounce, 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 bounce. A ball is very fluid. A ball will travel up, then it'll travel down, then it'll travel up, then it'll travel down. So far, I've only considered the possibility of the downwards path of the ball. So I also need to consider, what about the uptrend of the ball? What about the path that it takes once it's rebounded off the ground? Right? Obviously, this also has to exist. And what you can notice is the lines that I'm drawing in blue, they are the exact same distances as the lines traveled in red. If a ball goes up a certain height, it must come back down the exact same height. It must come back down the exact same distance. So what we can say is this height is going to be 10 meters, and this height is going to be 6.6 meters, and this height is going to be 2/3 of 6.6, 2/3 of the previous, 2/3 of the previous, and so on and so on. In other words, this summation is just for the red lines. So this is the direction, this is the distance traveled when the ball bounces down. And the distance that it travels up will be the exact same. So the summation to infinity for the blue bounces when it goes up after the rebound is also going to be 30 meters. Okay, so it's also going to be 30 meters. So we know that the total distance traveled along this entire path, okay, until infinity will equal 30 plus 30. So this distance will be convergent to 60 meters. But then we can also realize we have traveled an extra 15 meters on the first bounce. So the first bounce, we traveled 15 meters. So that means our final sum, right? So that means the total distance that we have actually traveled along this ball is going to equal to the initial 15 meters when we dropped it, plus the 30 meters that we gathered from the infinite downwards path of the ball to infinity, plus the 30 meters traveled by the infinite up path of the ball for each rebound. So if you work this out, the total distance traveled is simply going to equal to 75 meters. Okay, so this is what the total distance traveled by the ball will converge to, and this is how infinite geometric series work.